Okay, so we are discussing about the linear phase. So how this linear phase will be implemented in FIR filter, we will discuss. First let us start with that FIR filter, then we will go for that what do you understand by linear phase in a system, what is linear phase, why it is required, and what is the condition for linear phase in FIR filter, how it is possible to implement linear phase in FIR filter, those things we will discuss. So let us start with the FIR filter. So as I said, FIR filter is nothing but a finite impulse response filter. So this BK, I can say it is nothing but a filter coefficient which is represented by Hn. Understand not? So this is the Hz. So what is the output? Output is filter coefficient. So if I say a filter is a system, this is H of n, let us say, this is X of n. So in output is Y of n. So when I say what is Y of n, is nothing but a convolution between X of n and H of n. Convolution between X of n and H of n. So it is nothing but a convolution k equal to 0 to n minus 1 x of the H of n x of n minus k. So H of n is nothing but the filter coefficient. So that's why I can write in BK, filter coefficient, value, filter coefficient. So if I know the filter coefficient from the given specification of the filter, then I can implement the filter is nothing but a convolution of the signal with the filter coefficient. Let us say I want to implement a filter where the length of the filter is, let us say m, order of the filter is m. So in that case I have an H of n varies from 0 to m minus 1. I have a signal x of n whose length is, let us say, L, varies from 0 to L minus 1. Then what is the length of Y of n? What is the length of the convolution? I repeatedly said that the length of the convolution is nothing but a m plus L minus 1. During convolution and also during frequency response, the DFT, I have discussed about this one. Okay. Now if I take the Z transform of that, Z transform of the filter H of n, which is nothing but this one. This is the Z transform of H of n. Here n is the order of the filter. So the length of the impulse response is n. All poles are at 0. All poles are at 0, z to the power minus n. So it is 1 by z to the power n is nothing but all poles are at 0. 0 can be placed anywhere in the z plane. So this is the property of this z transform. Z to the power minus n, 1 by zn. So I can say this all poles are located at 0, at z equal to 0, because the solution of z to the power n is nothing but a z equal to 0. There may be a n number of poles, but all are in origin, and 0 can be placed anywhere because 0 is not there, 1 by z to the power n is only there. So 0 can be placed in anywhere. This is the z domain response of the impulse response of FIR filter. So ultimately our aim is to find out BK from the filter coefficient and compute convolution between BK and X of n minus k, or find out H of n from the given filter specification, and I have to compute convolution. Filter specification given in frequency domain. What is given to me? H of omega. That is given to me. It is not given to me H of n. So I have to convert H of omega to H of n based on the specification. Once I get H of n, my filter is nothing but a convolution between the input signal and H of n. Okay. Now if you see, so this is X of n. So this is a pictorial representation of this function, that Y of n is equal to k equal to 0 to n minus 1 h of n into x of n minus k. So now if you see, when I say y0 is nothing but a sum of k equal to 0 to n minus 1 h of 0 into x of 0 minus k. Okay. So x of n delayed by one sample. So I can say this, since this, if you see the z domain, what is hz? Hz is nothing but a n equal to 0 to n minus 1 h of n multiplied by z to the power minus n. Now if I say what is n equal to 0, so if I expand this summation, it is nothing but a h0 multiply z to the power minus 0 plus h0 multiply z to the power minus 1 plus h0 multiply z to the power minus 2. So z to the power minus 1 means one sample delay, minus 2 means two sample delay, minus n means n sample delay. So it is varies from n minus 1, so it will be n minus n plus 1 and n minus 1 sample delay. Okay. So I get this one, yn is equal to h0 into xn, h1 into x, one sample delay of the x. Then here h of n minus 2 sample delay of xn, and h of n minus 1 sample delay of xn. So I get this one convolution function. So if I want to represent in figure, how do I do that? So x of n multiply by h0 multiply with x of n, x of 0 and product and come to sum. h1 it will be multiply after this delayed by one sample. So h of n without delay, x of n multiply with h0, one sample delay multiply with h1, two sample delay multiply with h2, three sample delay multiply with h3, n minus 1 sample delay multiply with hn minus 1, and all are summed together to give me my yn. So I can say this is my structure 1 implementation. X of n applied, delayed by one sample, multiply with the filter coefficient and sum them, I get the yn. So this can be written in a program. X of n, I can, if I x of n is known, h0 is known, h1 is known, h2 is known, so I can represent this one in a nothing but an algorithm. Which is this algorithm? You represent this one, computation of the convolution. So now my filter is an algorithm. Now what is the important? How do I get this h value? What should be the value of h0? What should be the value of h1? What should be the value of h2 from the given specification of the filter? That is called FIR filter design. Okay. Now if you see another view, this can be implemented in frequency domain also. So as I know, the frequency yn is a convolution in time domain. So in frequency domain it is nothing but a multiplication. Okay or not? In time domain it is convolution. So frequency domain it is multiplication. So instead of I can say compute this convolution, I can say I have an xn. Okay. So this is hk. Let's say hk is the impulse response of the filter, and I have an hk, because order may not be same. This may be L number, order is L, this may be order is M. Then what, if the order is L here and M here, then what should be the length of the DFT? L minimum length is L plus M minus 1, which is equal to, let's say, N. So I can say I can do the n point DFT of xn. So I get what I will get? I will get capital XM. I can compute n point DFT of HK, I get capital HM. Third bracket or first bracket? Generally third bracket preferred. because discrete signal generally written in third bracket. Okay, so I can say that then I can, once I get HM and XM, I can multiply them, I get YM. So I multiply them in frequency domain. Then I can do inverse discrete Fourier transform, n point inverse discrete Fourier transform to get Yn. Or in time domain, I can direct convolute the, I can say that directly I can compute the convolution, I get Yn. So I can compute, I can implement the filter in frequency domain. Let's say since that H omega is given, so from H omega I derive HM, discrete frequency response, and then I compute the DFT of the input signal and multiply with HM, then compute inverse Fourier transform, I get Yn. So the complexity is that 2 times I have to compute DFT complexity. First is this DFT, second one is inverse DFT. Because HM will be given in frequency domain itself. So HK I do not require, HK is not given. I have given in only HM. So once I given in HM, I can directly take that DFT of Xn and I can calculate Xm and multiply them and take the inverse DFT, I get Yn. Because anyhow H omega is given, I will compute Hm and from there I will be compute IDFT and find out Hn. That is the procedure. So anyhow one DFT I am doing for designing filter, inverse Fourier transform, or I can do it inverse Fourier transform offline and calculate the filter coefficient. So the when I apply in online, the filter when is applied in real time, it doesn't spend time or computation of the filter coefficient. But if you change the specification, then again you have to compute the filter coefficient and store it. In the MATLAB you see that you have stored the filter coefficient, then you take the Xn and just take the convolution, you get the output of the filter. Okay. So this is the implementation strategy. Whatever you want, you can use it. Now I come the advantage. Why most of the time we are talking for the FIR filter? Many times we are not talking about the IIR filter implementation. In digital filter, mostly we are talking about the FIR filter. Why? Advantage is design with exact linear phase. Can be designed with exact linear phase. So what is the condition for linear phase? Linear phase is H of n must be equal to plus minus H of n minus n plus 1, or n minus H of n minus 1 minus n, plus minus H of n minus 1 minus n, symmetry or anti-symmetry filter function. So that is required exactly linear phase. So what is linear phase is important issue. We have to explain why this linear phase we are looking for. If it is not, what could be the reason? What could happen if it is not exact linear phase? That I have to understand. Then only I talk about the linear phase. Filter structure always stable with quantized coefficient, because here the pole zero concept, here only all zeros are, all poles are at origin. So within that unit circle is guaranteed. So filter structure is always stable. Now what is the disadvantage? The complexity. In the case the n is the FIR filter order, FIR filter is considerably higher than the order of n IIR filter. So the number of coefficient n, the computational complexity in case of FIR filter is much more compared to an IIR filter. Because if you see, when I put an hz, second order polynomial, how many delay is required? Z to the power minus 1 and Z to the power minus 2. But think about 350 coefficient FIR filter. So order is 350. So FIR, order of FIR divided by order of IIR, it is typically order of 10 or more. So 10 times much more complex than the IIR filter. But advantage, it can be easily designed for linear phase and it is always stable. So that's why we look for FIR filter for the first these two advantages, linear phase and stability. But yes, FIR filter is much more complex, computationally complex compared to IIR filter. Okay, now we come to that linear phase. What is linear phase? I am not reading the slide, you can read it. So linear phase is a property of a filter where phase response of the filter is a linear function of frequency. So you know the magnitude response, H omega mod of H omega magnitude response, and tan inverse, you know that tan inverse imaginary part divided by real part is the theta. So theta is also function of omega. So theta is called phase response. So as I draw the magnitude response like this, similarly I can draw the phase response also theta omega. Theta versus this axis is omega and this axis is theta omega. So this phase response must be a linear function of frequency. If it is not linear, what will happen? So filter is nothing but a system. If the system doesn't support the linear phase criteria, then if you see, if I apply a signal e to the power j omega, omega is a particular frequency, and another e to the power j omega 1, which is another frequency, if the phase are different, so at the output, if the phase is not predictable, omega and omega 1, if the phase is unpredictable phase, then I should not know that what should be the output component. They may come completely out of phase or completely in phase, I do not know. So that means the result is that frequency component of the input signal are shifted in time by the same constant amount. So I can say 1 kilo, the amount of shift. So what is phase? First of all, you have to understand what is phase. When I say a sine curve, let's start from here. Start from here. So this is start from 0. If the sine curve is start from here, so it is pi by 2 is the phase shift. So that is the phase. So if I say a signal is consist of sinusoidal component, every frequency. So if the every frequency is shifted in equal amount, then I know it is linear phase. If it is not, then the phase is not linear, then the frequency response will be, phase will be different for different frequency. So what is required? The group delay, first order derivative is linear, y equal to mx plus c, where the m is the slope, is the first order derivative of the phase response, which is nothing but a group delay. So what is required? If it is not linear phase, then different frequency component will be shifted in time indefinitely. Means somebody is shifted in 10 samples, somebody due to the phase change. So I apply a filter and the change of the phase, some frequency components start from this way, some frequency components start from here. So that will create an output signal distortion. So if I want linear phase, then what is required? The impulse response should be support this condition. H of n is equal to plus minus h of n minus 1 minus n. So, if it is plus, then it is symmetric response. If it is minus, it is called antisymmetric response. So, I can say both the phase and group delay in a linear phase filter are equal to n minus 1 by 2 sample for plain delay every frequency. So, n minus 1 by 2 is the exactly half of the total filter delay. So, what is the requirement in here? So, H0 must be equal to someone, let the order of the filter is 10. So, n minus 1 is 9. So, if it is H0, then this side will be H9, n equal to 0. Now, H1 should be equal to H of 8. So, n by 2, this side and that side of the impulse response are same. If they are same, then it is called symmetric filter, symmetric response. If they are in opposite phase, if it is H0 is equal to minus H9, then it is called antisymmetric filter. Now, I get the condition for which the filter will be linear phase. The impulse response must satisfy this criteria for linear phase. Now, let us go for the design of linear phase FIR filter. Okay? So, how do I design? What kind of frequency response will get if I design in linear phase filter? So, what is Hz? Hz is equal to n equal to 0 to n minus 1 h of n z to the power minus n. This is the z transform Hz. So, I can say this is nothing but a H0, H1 z to the power minus 1, H2 z to the power minus 2 plus dot 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 h of n minus 2 z to the power n minus 2, h of n minus 1 z to the power n minus 1. This if the order of the filter is n. What is the condition? H of n must be equal to n minus 1 minus n. Now, let us say the n is even, So, order is even. So, if the order is even, then n by 2. So, this side n by 2 is equal to this side n by 2. So, H0 to H n by 2. So, n by 2 number of from H0 and n by 2 to n minus 1. So, 0 to n by 2 minus 1 response is equal to the response of the n by 2 to n minus 1. If n is even divisible by 2. So, now if I take this factor is common from all h minus z minus n minus 1 divided by 2. So, how many samples are there? They are similar. H0 is similar with I said last. So, let us say forget about the n. Let us say take, okay, let us first compute for the normal n value and then come to this equation. Let us say I will take a slide here. So, let us say I said n is equal to 10. So, n is an even number. So, I can say the h of z, Hz is equal to H0 into z to the power 0 minus 0 plus H1 z to the power minus 1 plus H2 z to the power minus 2 plus, let us say instead of 10, so I have to write many things. Instead of 10, let us say it is 6, let us say 6. So, 0, 1, 2, 3 is there. So, H3 z to the power minus 3 plus H4 z to the power minus 4 plus H5 z to the power minus 5. So, if you see 1, 2, 3, 4, 5, 6. So 6 is the order. Now I said if I take z to the power minus n minus 1 by 2. So what is n? N is equal to 6. So n minus 1 divided by 2. So it is nothing but a 6 minus 1 by 2 is equal to nothing but a 5 by 2. So I take common minus z to the power minus 5 by 2, take common from this part. So here it is not there, so I can say H0 into z to the power plus 5 by 2 plus H1 into, there is a minus 1, I have taken common this one. So this will be added up 5 by 2. So it is nothing but a minus 2 plus 5 divided by 2. So it is nothing but a 3 by 2 plus H2. So it is nothing but a minus 2 plus 5 by 2, it is minus 4 plus 5, 1 by 2, z to the power 1 by 2 plus H3. So it is 3. So 3 plus 5 by 2 minus 3 plus 5 by 2. So it is nothing but minus 6 plus 5 divided by 2 is equal to minus 1 by 2. So it is nothing but a z to the power minus half plus H4 into z to the power minus 4 plus 5 by 2. So it is nothing but minus 8 plus 5 by 2. So it is equal to, it is nothing but a minus 3 by 2 plus H5. So minus 5 plus 5 by 2. So it is nothing but a minus 10 plus 5 divided by 2, minus 5 by 2, z to the power minus 5 by 2. If you see this component matching with this component matching with this component, which one? This component. This is matching with this component. So I can say, instead of writing n equal to 0 to n minus 1, I can say 0 to n by 2 minus 1. So it is varies from, so those are clubbed together. So I can group them, this component and this component can be grouped together. Only difference is plus minus. So this component and this component can be grouped together. This component and this component can be grouped together. So instead of writing z to the power minus 5 by 2, here n is equal to 0 to n minus 1, I can say n by 2 minus 1 h of n. Now I said z to the power, this one is positive, this one is negative. So this one is n minus 1 plus 2n plus minus z to the power. So this can be minus also. What I said, y of n is equal to h of n is equal to plus minus h of n minus 1 minus n. So if it is plus symmetry, minus symmetry. So H0 z to the power 5 by 2 can be equal to positive or plus minus, or it can be negative. If it is negative, then it is antisymmetric. If it is positive, then it is symmetric. So it is nothing but a z to the power minus n minus 1 plus 2n. If a small n is equal to 0, see that it is z to the power n, n means your 6, 6 minus 1 plus 0 divided by 2, sorry, divided by 2, by 2, which is nothing but a z to the power 5 by 2, and this is minus 5 by 2. So I can generalize if that. So it is nothing but a h of n z to the power n minus 1 minus 2n by 2 plus minus z to the power minus n minus 1 2n by 2. Clear? So if n is, sorry, if n is even, when the order is even. So for the order of 6, I have shown you order of 6 is okay. So when the n is even, the hz can be reduced to this one. Now if the n is odd, what will happen? Let us take it. So now I said n is odd. Let us say, take a small example, n is equal to 5. N is odd. So I can say Hz is equal to H0 z to the power minus 0 plus H1 z to the power minus 1 plus H2 z to the power minus 2 plus H3 z to the power minus 3 plus H4 z to the power minus 4. So 1, 2, 3, 4, 5 order is mentioned, 5 order, n is equal to 5. Now if I take n minus 1 divided by 2, what is n minus 1 divided by 2? 5 minus 1 divided by 2. So it is nothing but a 4 by 2 is equal to 2. So if I take z to the power minus 2 common, which is nothing but a n minus 1 divided by 2 minus. Okay. Then if you see this one, there is a 0. So I take minus 2. So I can say H0 into z to the power 2 plus H1 into z to the power 1 minus 1 plus 2, 1 plus H2, z is already taken out, plus H3 into z to the power minus 1 plus H4 into z to the power minus 2. Now if you see, except this coefficient, this one is matches with this one is matches with this one. So I can say z to the power minus 2 H2. So what is the general form of 2? Z to the power minus n minus 1 by 2. So if I want to write down the general form, so it is, what is the 2? It is nothing but a n minus 1 divided by 2. This no z is there. Rest are h of n. So how much sample is left? One sample is taken out. So out of 5 sample, one sample is taken out. How much is there? Only 4 is there. So I can say n equal to 0 to n minus 1 by 2. So 4 sample also it occur in pair. So 1 pair and 2 pair. So in case of 6, it is nothing but a 5, n equal to 5 minus 1 divided by 2. So 4 by 2. So n minus 1 divided by 2, h of n into z to the power, it is positive. So 2 n minus 1 minus 2 plus 2n plus minus z to the power minus n minus 1 plus 2n. If you see n equal to 0, so H0 z to the power n is 5 minus 1, so divided by 2 will be there, divided by 2. So it is nothing but a H0 into z square. Okay, understand or not? So I can say that generalized form for odd is nothing but this one. So if I apply this condition, then if the order of the filter is n is even, then the Z transform will be this one. If the order is odd, then the Z transform will be this one. Clearly understand, don't remember it. Clearly understand it, don't remember it. Is it clear? So I employed the situation, the requirement of linear phase filter. So linear phase requirement is this one. Plus minus is term of symmetry or antisymmetry. If it is symmetry, that means same side. If it is antisymmetry, it is the negative. So that's why once it is negative is antisymmetry, once it is positive is symmetry. But if n is odd, then one sample will be without z. If n is even, there will be one, see that one, no, none of the coefficient is without z. So for odd and even, I get two equations, equation 1 and equation 2. In the next class, let us try to derive what is the frequency characteristics of n is even and what is the frequency characteristics if n is odd. Because if I say Hz, so how do I get the frequency characteristics from Hz? Z is nothing but a complex function e to the power j omega. So if the amplitude is equal to 1, so if the mod of z is equal to 1, then I get h omega. So I put mod of j is equal to 1 condition and I derive the h omega. So what is the expression for h omega? Okay, so z is nothing but a r into e to the power minus theta n or omega n. Okay, so z is a complex number, j, there will be j omega n. So r is 1, that means amplitude is 1, all frequency component has unit amplitude, and then I get the frequency response of h omega, because I said that I want pass band all 1 and stop band all 0. So if in all frequency component unit amplitude is 1, but phase will be there. So what will be the frequency response for n order is even and odd will be derived in the next class. Okay, thank you.